Recording in progress. All right, guys. Let's do a quick recap of what we have learned so far. Okay. First things first, we understand that waves are basically coming in two, right? It is either a transverse wave or it is going to be a longitudinal wave. Now, in terms of a transverse wave, I mentioned a few key points here: the crest, the trough, the amplitude, and then the wavelength. All these things you must know by now. For those who do not know, please make sure you go read it up. Okay, the amplitude is very commonly responsible for the loudness of the sound. Guys, the loudness is very important, and the frequency obviously relates to the pitch, right? From here, we also learned that it's V equals to F lambda. This is the only formula you have learned so far. Then we also learned about a longitudinal waves where it has compressions, where it is a region of high pressure. That's why the molecules are closer together. And rarefactions, where it is a region of low pressure. That's why the molecules are further apart, guys. If your IGCSEs ever ask you to define a longitudinal wave, you have to define it in terms of its vibration and propagation, guys. For a longitudinal wave, the vibration will be parallel to its propagation here, right? So it's going to go left, right, 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 and so on, right? Whereas a transverse wave will have vibration perpendicular to its propagation. Here you can see that it goes up, down, up, down, up, down, right? So it goes up, down, up, down, up, down, up, down, up, down, up, down, and so on, right? Every other wave beside sound wave and ultrasound is supposed to be a transverse wave, guys. You'll see this very, very often in your paper 2, which is essentially 3 marks, right? Because you know for a fact that sound waves and ultrasound are the only longitudinal wave. Every other wave under the sky is supposed to be a transverse wave, be it water wave, light wave, electromagnetic wave, even if you, yeah. But anyways, so, guys, this is the transverse wave. Then last week we also learned about the 3 phenomena, right? We talked about reflection, refraction, and also diffraction here. I introduced you guys to wave fronts. Guys, if you see the word wave fronts, guys, is basically just stating that it's like the top view of the wave, right? These are all the crest. All these are wave fronts, right? So I also mentioned that for reflection, the angle is always with reference to the normal, guys. The normal is an imaginary line, right? That is directly perpendicular where the light hits. So if the light hits here, it's going to create a normal, and this is supposed to be your incident angle, and this is supposed to be your reflected angle. For law of reflection, obviously the incident angle is supposed to be equals to the reflected angle, right, guys? And then for reflection, refraction, and diffraction, guys, I mentioned that something never ever changes. What's that something that never ever changes? Lucas. What's the something that never ever changes? Remember what I said, very important, always comes out in your exam one away. Lucas. Oh, Lucas, are you there now? Oh, this is not Lucas. But yes, Jerry, you are correct. It is definitely supposed to be the frequency, guys. Yeah. It's supposed to be the frequency, guys. In your exam, they'll always ask you what never changes. Does frequency change or something along the lines? Doesn't matter if it's a reflection, refraction, or diffraction. The frequency never ever changes, guys. Very, very important. You must know this by now. Okay. Then, yeah. Please read the notes out for those who are still uncertain. For refraction of wave is something very important as well. I remember telling you a story, right, guys? Who can tell me what story it was again? Scott. Scott, what story did we talk about to remember how refraction occurs in a water wave? Where were you standing again? Where is this again now? Wait. Remember not? Wait, Scott. You there now, Scott? Oh my God, why is everyone AFK? On land? No, this is a beach, bro. This is the beach. Remember, this is the story of the beach. Imagine yourself in the beach, and from super far away, we said that the waves are, guys. The waves is like super damn tall, and then as it comes closer and closer and closer, it becomes smaller and smaller and smaller. What was the reason for this again? Kunling, what was the reason for this? Why is the wave so damn tall here, and why is the wave so damn short here when it's closer to the beach? What's going on? Speed or something. Yeah, good. It's definitely the speed or something. And what was the speed here? And what was the speed here? Oh, Hannah is in the mall, right? So let's ask someone. Natalie, which one was higher speed and which one is lower speed again? Huh? I wonder. You better know this. Natalie. Hey, who here can tell me the answer? Which one has higher speed and which one has lower speed? Deep high, very good, Jay. Excellent. You have saved her ass once again, right? The speed here is higher and the speed here is lower. Simply because in a deep region, we associate that the speed is much faster. That's why the wave is so damn tall. And in a shallow region, the speeds are much slower. That's why it's so damn short here, guys. Very, very important. This is like the basic understanding of how refraction occurs in a water wave. Anyone don't know what I'm talking about for this? Hey guys, this is very important. You need to know. Hey, just read the notes. Everything is here already. And everything else changes for refraction. Frequency is the only thing that doesn't change. Everything else changes. You can refer to this one here. Right. Then after that, we also talked about diffraction. Diffraction is essentially the spreading of the wave, guys. It is the spread. Oh, I just noticed that, Hannah, you have quite a funny description of yourself. It's a they or she kind of thing, is it? But anyways, diffraction is essentially the spreading of the waves, right? It basically, the spreading depends on one specific thing. What is that one specific thing that causes diffraction to occur more? Oh, back to rotation. Lucas, are you back already? No, Lucas, are you there today?
Yeah, I'm back, sir. Sorry, I just came back home from school.
Oh, okay. All right. Now, since you're back, right? What was the reason for the spreading of the wave again? What causes the diffraction to occur more again? Do you still remember from last week?
The gap.
More specifically, the gap definitely affects the spreading, but which one?
When the gap is smaller, the diffraction is larger.
True, that is definitely true. But yeah, it's basically here. But guys, pay attention. The gap is only a factor that affects the spreading. The real factor that affects the spreading is actually supposed to be the wavelength. Now, guys, pay attention. It's the wavelength. The larger the wavelength, usually diffraction will occur more. That's why you see, I mean, this drawing is a bit shitty, right? But you gotta imagine this one. You gotta imagine that this wavelength is damn long and this wavelength is damn short. And because this wavelength is damn long, you can see that it actually diffracts more. This one, the wavelength is damn short. That's why it diffracts less. In other words, this one spreads more, this one spreads less, because the wavelength is longer, guys. Very, very important. The wavelength is the one that affects the diffraction of the wave. And everything else is the same for reflection. This is the exact same as your reflection, guys. Make sure you know this. All right. Nothing much to explain here. Then after that, I ended the class with giving you guys some homework and doing some art class, if I do say so myself, right? All right, I just want to know, right? Dare I ask, how many of you guys actually finished the homework from here? How many of you guys actually did the homework from here? Can I have a raise of hands for those who actually finished the homework from here? One, two. I forgot, bro. Am I surprised, Kunling? Am I really surprised? Hey, you got to do the work, bro. Bro, guys. How about Scott? How about Lucas? You guys gonna do or not? You go fire. All right, guys. I have to emphasize this since you guys are going into year 11, guys. I mean, okay, like realistically, right? I was a student once as well, and I was in year 10 as well. And obviously, I was definitely not the model student myself, right? Year 10 is like it's like the neither here nor there year, you know, it's the perfect honeymoon year. Whatever you do, no one cares. Whatever you don't do, no one cares as well. But let me tell you, as we enter next month, right, where you guys will officially be year 11, right? Yes, definitely. Right. As you enter year 11, right, guys, I want to emphasize that attempting the question is highly, highly, highly appreciated. Why? Because physics is just like mathematics, you know. If you watch someone do it, it always makes sense. For sure, it will make sense because the guy that is doing it is the one that's teaching you, right? But when you're doing it yourself, it's a totally different experience, guys. You need to do the exercises, then you'll understand what is going on. And I recommend doing it consistently, because if you don't do it now, it's like you're borrowing happiness, you know. Of course, it's fine, it's fun and games when you don't need to do it, then you can go do your own things, right? But this is a borrowed happiness, you know. You'll have to repay it sometime along the line. You know, as you go into year 11, some students, if they are mentally strong, and they'll say that, okay, I've played all my year 10, I'll focus more on year 11, right? Then that's normal, that's very good, right? But for those who are a little bit more weak-minded, they'll be like, oh shit, I don't know anything. It's time to give up, guys. And then they start to proceed to drop the subject. Or they'll just struggle because their parents kind of force them to not drop the subject. Hey, but hey, guys, let me tell you, physics is actually very, very easy. Okay, what race is bloody but anyways, physics is actually very easy, but it definitely requires you to put in effort, guys. So yeah, just a little nagging here and there, right? It's always good. Anyways, for those who have done the exercises, congratulations, keep it up. The effort will pay off eventually. All right. Yeah, moving on from this here. So if you look at this question here, a device at the bottom of the sea emits a sound wave of frequency 200 Hertz. First and foremost, you identify your information. They say that the speed of the sound is this amount, right? And they ask you to calculate the wavelength. Looking at these three components here, the only formula that I can form is obviously the V equals to F lambda formula, right? From here, if I'm looking for lambda, it will be essentially V over F. That's why it's going to be 1,500 divided by 200. And thus you should find 7.5 meters as your answer. For those who did not attempt it, please write down at least the answer and attempt it later on and see if you had the capability of getting your own answer, guys. It's very important. If you don't do it, then it's just GG town. Anyways. The sound wave passes through the sea into the air. State what happens, if anything, to the frequency. Guys, what's going to happen to the frequency? It is the same answer and same question every time. The frequency remains the same. Or if you've written down unchanged or does not change or anything along the lines, it doesn't matter as long as you know that it did not change, guys. And from here, if the frequency remains unchanged, next thing they want you to find is the speed of the sound. As the sound goes from sea into air, because the molecules are further apart, guys, you know, like how air molecules are like this, and then water molecules are closer together, right? Obviously, sound travels much faster here, guys. That's why you're supposed to say that as it enters from sea into air, the speed of wave actually slows down, right? Or decreases, or whatever way to say that it went down, right? And that is going to be your answer, guys. Right? Quite straightforward. From here, easy question. And after that, name the process that takes place at a boundary. The boundary is this boundary, by the way, guys, for those who are a bit confused. I always have students don't understand this word boundary. A boundary is like the boundary between the shallow and deep region. between the shallow and deep region here. All right, name this process. This is obviously supposed to be refraction of the wave. And yet again, you'll see another free mark. Which one of it remains the same in shallow and deep? It is always going to be the same answer over and over and over and over again, right? It's the frequency that always remains unchanged. So yet again, 3 marks. Then from here, a sound wave traveling in air approaches a solid barrier with a gap in the middle. Figure 6.1 represents the compression and rarefaction of the sound wave. The compressions are labeled A, B, C. Compression, compression, compression. State how a compression differs from a rarefaction here. Guys, if they ever ask you to talk about compression and rarefaction, you are expected to explain it in terms of the pressure, guys. Just like I mentioned, compression is what again, and rarefaction is what again in terms of pressure. Scott, how does the pressure differ for a compression and rarefaction again? Scott. Compression is a region of high pressure. Excellent. That is the answer here. Compression is a region of high pressure where molecules are closer together, and rarefaction is a region of much lower pressure. That's why the molecules are further apart. This is a standard answer, guys. It is very commonly asked in your IGs as well. So you definitely need to know this, yeah. All right. Then from here, they say that the speed of the sound is 340 meters per second. The frequency is this amount. Yet again, I have V and F. Definitely, they are going to ask me to find lambda, right? Because according to the V equals to F lambda, lambda would have been V over F yet again, right? So it's going to be 340 divided by 850. Press that in your calculator, and I think you'll end up with 0.4. Yeah. It's going to be 0.4 meters, guys, meaning to say A to B, because it's as soon as it repeats itself, guys, A to B is going to be considered as 0.4 meters here, compression to compression, guys. Then the next part here, they say that the time elapsed before compression A reaches the barrier. This word is also another fancy term, right, to say how long it took, you know, like how long the time passed for compression A to reach barrier B. Sorry, this barrier here, right? This barrier A is supposed to reach, sorry, this compression A is supposed to reach this barrier here, right? And they ask you for the time. If I ask the time and I'm given the speed, obviously the first formula that I will think about is supposed to be the speed equals the distance over time formula. And from there, time would have been obviously distance over speed. For those who wrote distance of 0.4, you are gravely mistaken. Why? Because the distance is from A to the barrier and not the wavelength. This is 0.4. Here is another 0.4 and 0.2, which gives you a total of 1 meter here, right? And the speed is still the same. It's going to be 340 meters per second. Press that into your calculator and you would have gotten a very big number, 2.9 times 10 to the power of -3. seconds. Okay, you're supposed to get 2.9 times 10 to the power of -3 seconds, guys. All right, then finally, they say that on figure, oh, not finally, figure 6.1, draw the shape and position of the compression of B and C as A reaches the barrier. Right now, according to this statement here, A has reached the barrier already, meaning to say the compressions B and C have passed through, meaning to say if I am supposed to draw in a normal scenario, guys, listen up. In a normal scenario, I'm expected to draw at least 3 diffracted waves. Okay, this is like the standard law of God, you know, it's supposed to be 3 diffracted waves. But in this question here, because they only say that B and C pass through the barrier, you are only expected to draw 2 waves instead, guys. And because you're expected to draw 2 waves, you have to draw 1 wave here and another wave here. Now, when you draw the waves, it's not just suka hati as well, right? It is supposed to be something relevant to the mark scheme. When you're drawing the diffracted waves, the first criteria is that the first wave must be from the opening, meaning to say, if you drew from here to here, or you drew from here to here, these two would be definitely wrong, right? So it's supposed to be at the opening here. The second thing that you must be careful of is the wavelength, guys, because diffraction does not change the wavelength, right? And because it does not change the wavelength, when you're drawing the diffracted wave, you are expected to draw at least from the eye level. If it doesn't look, if it is not measured exactly the same 0.4, it's fine. But from the eye level, it seems as though it is 0.4 meters, guys. And this is how you're supposed to do this question here, guys. It's supposed to be 0.4 here, all right? I mean, at least from the eye level. If you draw something like this, then good luck, have fun, right? It's definitely going to be wrong. You have to draw it at least looking like 0.4. Of course, you can draw it much better with a pencil. I'm just drawing with a mouse today, so it looks kind of bad. But yeah, two things to be careful of, guys. It should be from the opening. It should be from the opening here, and the wavelength should be the same. In fact, I'm sure the mark scheme says something similar as well. You see, two circular arcs centered in the midpoint of the gap in the barrier by I. By I means to say roughly, right? Along the center, arc separated the same distance as the adjacent compression, right? Exactly the two things that I mentioned here. And that is why it is 2 marks, right? And finally, the sound wave also travels in water. State how the speed of sound compares to speed of air. You're supposed to say something like the speed of sound in water is much faster than in air. Hey guys, who can tell me the speed of sounds in different mediums again? Now, what's the speed of sound in air, liquid, and gas? Anyone? Actually, when I say anyone, I mean Hannah. What's the speed of sound in air, liquid, and gas again? Are you back? Are you home yet, by the way? Oh. Very good. I assume. Yeah. Yeah, Jerry's got the right answer. Who else do I want to pinpoint? And Natalie, you better know this. What's the speed of sound in air, liquid, and gas? 330. And this one? 150, 1,500. And this one? Oh, it's solid, guys. Solid. How much in solid? Where got 30,000 so much, bro? It's 23,000. Guys, how do you remember this? You remember the basic one first, which is 330, right? From here to here, you multiply 5. From here to here, you multiply 10. This is how you get the rough answers for the speed of sound. And this is very important. For those who don't remember it, you have to know this. It's kind of like expected of you to know it for some reason. So it's just a multiple of 5 and a multiple of 10. Very, very important. Okay. Then moving on to the next part here, which is essentially the last question really. Okay, a dolphin produces a sound wave in a frequency of this amount here. Figure 6.1 represents the rarefaction of the sound wave traveling in the water hitting the side. State what is meant by rarefaction. Now, guys, a lot of students when they see this drawing and then they see this word, right, automatic, their brain don't read the full statement already. A lot of you guys, in fact, maybe some of you guys may have read this as a rarefaction. And from here, you might have even said that it is a region of low pressure. Refraction. Sorry, you might have written down refraction. It might have written down refraction's definition, which is due to the change in speed of the wave. Guys, a lot of students, they make this mistake, guys. This is not refraction. This is rarefaction. And rarefaction is the region of low pressure. That's why the molecules are further apart. Don't write it is due to the change in speed of wave, guys. That's refraction. That's refraction. This one here. Refraction. This is a refraction. The one that we are looking at right now is rarefaction, and refraction. Very common mistake between the students are they always give me a random answer here, but let's read the question properly, right? So from here, region of low pressure. Thus molecules further apart. Okay. Yes, same definition every time. That's why it's very important, right? And finally, they ask you here, figure 6.12 refractions A and B. This is a rarefaction and this is a rarefaction, right? And they say that each and every one of these are a rarefaction. From here, the first things first is this is one wavelength, this is another wavelength, another wavelength here. Okay. And I say that two refractions are labeled, the distance between A and B is 0.76, right? 0.76. Then they ask you for the wavelength, right? How many wavelengths are there? One wavelength, two wavelength, three wavelength, four wavelength. 0.76 over 4 would have given you 0.19 meters, guys. This is your wavelength for this wave here, right? Then yet again, they ask you for the time taken for the refraction at A to reach the point B here, right? So again, if you're looking for time and you have the speed, oh, you don't have the speed, you have the frequency, right? Obviously, if I'm looking for time, it's supposed to be speed equals to distance over time. And from here, in order to use this formula, I must be given this and this. I have the distance, A to B is about 0.76 as stated from the question. But I don't have the speed, right? But because I don't have the speed, I have the frequency and the wavelength, means to say I have to find the speed myself, right? Which is according to the V equals to F lambda formula. Yet again, from here, the frequency would have been 7,800. The wavelength would have been 0.19. Press that into your calculator, substitute this number into this number here. You will be able to find the time, right? And your time should be somewhere around much. Oh, a very weird number again. 5.13 times 10 to the power of -4. 5.13 times 10 to the power of -4. And make sure you write your units, guys. Make sure you write your units. Because if you don't write your units, it's just end. Just end. All right. Anyone's got any questions for this calculation part here? Anyone don't know what I'm talking about? Good. 100% absorption rate. Just what I like. And finally, in the last part here. The last part here, the sound wave passes from the wood, where the speed of sound is greater. What happens to the frequency? Oh my God, 3 marks again, stays the same, right? Wait, how to do the last question again? What? I just explained this in time. Yeah, I'm supposed to use the cone length. You're supposed to use the speed equals to distance over time formula, right? Then if you're looking for the time, obviously you must be given the speed and distance, right? The distance I know for a fact is this amount already. I want to find the speed. I don't have the speed because I'm given the frequency and the wavelength. If I'm given the frequency and the wavelength, I can use the V equals to F lambda to find the speed. With this speed, I can substitute this into here, right? With this information, with this and this, I am able to find the time. Do you know what I'm talking about? Bro. Yeah. Right. Hey, yeah, copy it down if you're uncertain. Okay, anyways, moving on. Very good. Moving on, they ask you what's the wavelength here, right? And if they ask you what's the wavelength, then, oh, sorry, what happens to the wavelength? If they say that the speed of sound is greater already, if you follow the V equals to F lambda formula, if my frequency stays the same, as soon as my velocity increases, my wavelength is bound to follow. Anyone here having a hard time understanding this? You want me to show you in terms of numbers? Anyone don't understand this one here? Yes, good. If that's the case, then obviously you're supposed to say that the wavelength increases. Okay. And finally, from here, they ask you on figure 6.1, sketch the position in the wood of the three incompleted refractions. In the wood, they already say that the speed of sound is greater. So if I'm asked to draw this kind of questions again, yet again, originally it's supposed to be dot, 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 like this, right? My question is this: will the waves lag behind or will the waves lead forward? Who have I not asked yet right now? Hannah, will it lead forward or will it lag behind if the speed of the wave increases? No, lag, no. Bro, it's leading forward. It's supposed to lead forward. Why? Because the speed of the wave is increased. Remember or not? I told you, if let's say they ask you to draw those stupid things, right? It depends on whether the speed is faster or slower, If this is the original wave, right? If the speed of the wave is faster, for example, this is the deep region, then it's supposed to lead forward. If it is a shallow region, instead, it's supposed to lag behind because the speed of the wave is slower already. Remember or not? Very important, this one here, right? So from here, you're supposed to draw this. Right? You're supposed to draw three waves that are leading forward. Then you would essentially get 3 2 yet again. Okay, go to body. Okay, yeah. Anyone's got any questions from this exercise here? Anyone don't understand any specific thing or want me to clarify anything or want me to rephrase anything that we have mentioned so far? Okay, good. It's always good to have 100% absorption rate. And if that's the case, then moving on, we are going to the new chapter already, which is going to be light waves here. Light waves, light waves, light waves, light waves here. Yeah, I've sent the digital copy to the group already, guys. For those who did not notice, please go open up the file from there. For Lucas and Scott, actually next chapter onwards, I'll be sending you a booklet because this is already the end of year 10 already. That's why I'm not sending the booklet. But when you go into the year 11 class, you'll be receiving a booklet. But yeah, for now you'll just have to print it up because you joined very late. Okay. Yeah. Moving on to this next chapter here. This is essentially supposed to be the light wave chapter, guys. The light wave chapter is a very similar like the water wave chapter, but instead of 3 phenomena, light can only go through 2 phenomena in your syllabus. It still goes through diffraction, but it's not in your syllabus, so you don't need to know about that. For light waves, guys, it will only either go through reflection or it will go through refraction only. Okay. Now, if we want to understand how light waves behaves in terms of reflection, right? You can definitely imagine yourself standing in front of the mirror. I'm pretty sure all you vain people here have stood in front of the mirror and what's it called? Admire your own beauty. But anyways, right, if you ever stood in front of a mirror, you'll notice that in the mirror, if let's say, guys, if you stand in front of the mirror and you raise your right hand, the guy that is standing in the mirror will raise his left hand instead, right? This phenomena is something, this phenomena is something we call laterally inverted, laterally inverted. You know, like how to be inverted is to be upside down, right? Laterally inverted is to be left side right. I repeat, inverted is to be upside down, right? Laterally inverted is a left side right, guys. Very, very important. And this is the reason why when you raise your right hand, the guy in the mirror will be raising his left hand here, right? But of course, this is definitely not something your IGCSE will ask you. They will instead ask you how the image is formed from the mirror itself. Okay, now if I were to draw a simple light ray, which will not be in your exam, by the way, because it's too simple. The reason why there is this point here, this point of interest, right, is because the light is traveling into the mirror and it virtually goes to this spot here, right? This is how the light rays are behaving in the mirror. But in your IGCSEs, they'll never ask you to draw one light ray only. They'll always ask you to draw two light rays. And if you're asked to draw two light rays, guys, please pay attention. A lot of students always forget this. If you're asked to draw two light rays, first and foremost, you draw a small V sign here. Not V sign, like a weird 90-degree tilted V. Okay, you always start off with a weird 90-degree tilted V. These are supposed to represent your light rays. When the light ray goes here, right, because this is a mirror, right, the real light will be reflected away. When the light ray goes here, because this is a mirror, the real light ray will be reflected away. Now, bear in mind that mirrors will never absorb the light rays, guys. The reason why we see light in the mirror is because these are actually virtual light, guys. Virtual light means to say that we assume that the light ray actually is like going in like this. This light ray itself is actually just a reflection of this part here, guys. So when you draw this, right, what you are expected to do is you're expected to draw, once you have the reflected ray, you're actually supposed to draw virtual light ray that is supposed to be in one straight line with this, by the way. You're drawing one virtual light ray to the back here, and you're supposed to draw one virtual light ray towards this back here. Wherever these two lines meet, this is essentially where your image will be formed. This is your object. This is going to be your image, okay? Now, guys, very, very important. Sometimes I see students, they draw the virtual light here and the virtual light here. Oh, if the virtual is going this way, where the hell am I going to find the image, right? It doesn't make sense, right? So the idea is you want the light rays to converge, so you know where the position of the image is going to be, guys. Very, very important. Make sure you know this, okay? Anyone confused with this part here? Anyone don't know what I'm talking about? Okay. If you're not confused with anything I'm talking about, this will be a more beautified drawing now, right? So essentially, this is the object. They're drawing 6 light rays here. You'll never be asked to draw 6 light rays. You're only expected to draw 2. So you can pick either 2. It doesn't really matter, right? So this is the object. The light rays are all going to hit the mirror. All this real light, because it's a mirror, right, will be reflected out of the mirror. And then how is the image formed? The image is only formed when we assume that the light is going into the mirror. These are what we call the virtual light. You'll notice that it doesn't matter how many light rays you draw, they will still all intersect at the exact same point. And because it intersects at the exact same point, this is essentially where the image will be formed. Okay, everyone? Make sure you know this is actually super important, guys. You're expected to draw, by the way. You know how they'll ask you to draw in the exam? They'll give you something like this. Okay, right now, this is the mirror, right? This is the mirror. Then they say that, okay, right now, I have an object here. Find where the image is. If you're asked to find the image, and the object is here, what you have to do is you actually have to do 2 light rays, guys. You have to draw 1 light ray that goes up like this. Obviously, then this is the normal, right? It will be reflected at the exact same angle. Then you're expected to draw another light ray somewhere around here. And then it's actually going to give you the exact same angle as well, right? It's going to give you the exact same angle. This angle and this angle, this angle and this angle here is going to be the same. This is where your eye will be, and your image will be formed when you dot, 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 dot. And then you'll notice that this point where it dots will be exactly on top of where the object is, and meaning to say, this is where your image will be, and this is where your image will be. It will be expected to draw the light rays, so always remember this. It's actually very, very important. Okay, so from here, yeah, the statement is the same also. Image form from a plane is always virtual / laterally inverted. Okay, an image is said to be virtual when the light ray does not actually pass through the location on the other side of the mirror. It only appears to the observer as though the light is coming from the object, from the location. Guys, these light rays are not real light. It's virtual light. It is essentially a reflection of this light, this light, this light, this light, this light, and also this light. It's just a reflection, guys. It's not real. Okay, so same thing now. The law of reflection is applicable here as well, right? The angle of incidence must be equal to the angle of reflection. If this is your incident angle, sorry, if this is your incident ray, this will be your incident angle here. If this is your reflected ray, then this will be your reflected angle. And you'll notice that all these angles is yet again with reference to the normal here, guys. Super important. If I ever see any one of you guys draw this as your incident angle or this as your reflected angle, I will beat you if you ever come to the physical classes. But anyways, yeah. Yeah, the incident ray, the reflected ray, and the normal all lie on the same plane. You'll notice that the incident ray, the normal, the reflected, and all these angles here are all from the same plane. Nothing goes through the mirror, guys. Nothing at all. So they will all lie on the same plane. Okay. Anyone's got any questions from this part here? Anyone unclear with anything I've mentioned so far? Okay. So having said that, refraction of light wave. This is actually one of my favorite chapters here. Okay, guys, if you want to understand refraction of light wave, it's the same reason like how refraction occurs in the water wave, guys. By definition, refraction only occurs because there is a change in the speed of light, guys. What do I mean by that? Oh, check the word. Yeah. Anyways, if you want to understand refraction, you can always refer it back to the scenario where you looked at the straw in the water. You know, like if you ever have a straw in the water or a spoon or whatever nonsense in the water, you'll see that the straw or whatever thing kind of bends inside, right? It doesn't like go one straight line down. It kind of bend inside. The reason why there is a bending here is because there is a change in speed of the light. If your eye is here, right, the speed of light that you see here, right, is essentially going to be 3 × 10⁸ meters per second. This is just the normal speed of light. But the way that you see this here, the speed of light is definitely slower because it enters a different medium. So maybe you'll see this at 2 × 10⁸ meters per second. And because of the difference in the speed of light here, you will definitely see a difference in the object here. Whenever we talk about refraction, refraction occurs due to the change in speed of light. Okay. Now, a very common example of refraction is if you ever stood on top of a swimming pool before. Have you guys ever experienced this before? You're in a new swimming pool and then you're standing on top here, right? And this is the water. It's the water. All right. When you're standing on top of a swimming pool and you kind of like look down and then you're like, oh, it's kind of shallow, right? It's kind of shallow. Then when you jump down and then you realize that, oh shit, it's much deeper than it actually is. You know why it always seems like it's much deeper than it really is? It's simply because our brain, guys, perceives light to travel in a straight line. But the real light, when it enters a medium, actually changes direction and speed. So what happens is, right, when we look into the swimming pool, right, we assume that light is actually going to travel in a straight line here, right? But in reality, because the speed of light changes, what happens is, right, it actually bends and slows down, and then it reaches here. So this length here will be the exact same length here. This is the real depth of the water, but our brain perceives light to travel in a straight line. That's why we always think that this is the imaginary depth of the water. We think it's much more shallow than it really is because we don't register the light bending in water. Anyone don't know what I'm talking about for this part here? Very important. Anyone don't know what I'm talking about? This is very, very important. The light bends when it enters a different medium, right? But we perceive light to travel in a straight line. Of course, in IGCSEs, they will never ask you to draw just one light ray diagram. Never in a million years, unless you're really, really lucky, right? So instead of drawing one light ray diagrams, they'll ask you to draw two light ray diagrams. If they ever ask you to draw two light ray diagrams, so let's imagine, right? Let's imagine this is the point of interest here, right? If they ask you to draw two light ray diagrams, usually they'll give you like some eye here, the eye here, something like that. Right? When you're drawing the light rays, you yet again have to draw the two light rays. A lot of students, they like to draw from the eye here, which I highly do not recommend. I would much prefer you to draw it from the object itself. When you draw the object, yet again, it's going to be the V-shaped thing here, right? And obviously, as it enters a different medium, it's actually supposed to bend. It's supposed to bend, guys. It's actually supposed to bend. It's supposed to cause the light to bend a bit, right? And because the light bends a bit, right, what you're expected to do is this one bends and this one bends, right? So you're expected to draw the dotted line to complete. You're supposed to complete the light rays traveling in straight line here. And when you have that, this is where your image is supposed to be, guys. This is the reason why it looks much more shallow than it really is. It's because light travels at a different speed in a different medium, but our brain perceives it to travel in a straight line here. We perceive it to travel in a straight line, but it is definitely not that scenario here. Okay. Of course, if you want to look at a more beautifully drawn diagram, you can refer to the ones in your notes here, right? This is the goldfish, right? This is the light rays that are coming from the eye. We assume that light is traveling in a straight line, so we think that the goldfish is here, but in reality, the light ray has actually bended, but we did not register this in our minds. That's why we always see that the fish or the depth of the pool is always much more shallow than it is. Okay, so yeah, this is what you're supposed to know. Refraction occurs when light travels from one medium to another. When I say medium, I guess, oh, sorry, that's a question. Teacher, only human eye cannot, or other eyes also cannot. Actually, it's not a matter of can or cannot. It's just that our brain, because we like to believe that we are more sophisticated animals, right? But we're still just animals here. Our brain have always perceived light to travel in a straight line because everything in our life has always been true. The light is supposed to travel in a straight line, but when it enters a different medium, the light actually bends. So our brain, right, actually thinks that it's traveling in a straight line. That's why we'll never see where the real object is, right? And this is why the image is formed here. It's not just human eye. Everyone would have been the same thing as well, but it's just that the brain, the human being, thinks more. That's why it always seems like it's this. Definitely not. It's definitely not. Okay, but anyways, from here, yeah, different mediums. When we say one medium to another, I'm referring to air as one medium and water as a different medium. In your exams, if you ever see the word medium, please know that they're referring to either the air, the water, the glass, or the plastic that we can see through. That's the medium, guys. So obviously, yeah, when it travels from one medium to another, the speed is actually going to change, right? And that's why you have this here. Okay. Yeah, can you do it then? Yeah. Hold on, guys. I have visitors. Give me a minute. Okay, everyone, I'm back. Yeah, 5 minutes left. Okay, so yeah, I can read through this yourself. The last part I want to talk about today is basically teaching you how to see whether the light ray is going to bend closer or away from the normal, guys. This is the same application as the water waves as well, guys. First and foremost, you need to understand how the light rays are going to behave. Okay, so let's imagine today I have a glass block here. We have a glass block here. This glass block. Okay, and I have a light ray entering from one side and then coming out from the other side. And because it enters from one side, I'll say that this is the normal for the first part. And then as it goes from the air into the glass, guys, what do you think is going to happen? Do you think the speed of wave is going to be faster or slower? Let's see. Lucas, do you think the speed of wave is going to be faster in the glass or is it going to be slower in the glass?
Same.
No, it's definitely not the same, bro. What did I just tell you? Scott, what do you think? Is it going to be faster or slower in the glass? Slower, excellent. And because, why is it slower? Is because this glass is definitely more dense than the air. You know, like in terms of particle, it's much more dense, right? The light ray will have a harder time passing through the air particles only, right? So because of that, because the glass is much more dense, what's going to happen is the speed of the wave actually slows down. And because the speed of the wave slows down, originally, this was the original path, right? Because yet again, it slows down, it's going to cause it to lag behind. And this is what we call bending closer towards the normal, okay? The light ray is going to bend closer towards the normal. And because it hits here, right, yet again, there'll be another normal here, okay? As the light ray leaves the glass, guys, obviously what's going to happen is the speed of the wave is faster yet again. And if originally this was the supposedly trajectory of this light ray, right? Because it is yet again faster right now, it will bend away from the normal and lead forward. It will be something like this here, okay? Now, one thing I want to highlight is that this angle, because it is in the air, will be the same angle as this in the air, meaning to say these two lines are actually parallel to each other, guys. And because these two are parallel to each other, what's going to happen is obviously this angle here and this angle here would have been the same. Now, from here, this is the last takeaway for this lesson, guys. As light enters from less dense, which is air, to more dense, which is glass, the light is actually going to bend closer towards the normal. Whereas when the light enters from the more dense to air, which is less dense, it will actually bend away from the normal, guys. Yet again, it's the same thing. This here, the speed is fast. Here, the speed is fast. Here, the speed is slow. That's why it bends here. All right. Anyone don't know what I'm talking about for this part here? Anyone don't know what I'm talking about here? Oh, this is very important, I think. All right. So, having said that, Yeah, can you use the rest of the 2 minutes to copy down whatever you have? Look at this, the first example. This is when the light ray enters perpendicularly against the glass block. If it enters perpendicularly against the glass block, it will not refract into a different angle. It will just go straight through. A light passing through a glass block at right angles to the surface will not be refracted. The rays will pass straight through. When light travels from air, which is less dense, not less dense, is less dense, right, to glass, which is obviously more dense, light will bend towards the normal. It's going to bend towards the normal here, right? When light travels from more dense material to less dense material, light will bend away from the normal. It will bend away from the normal here. Guys, copy down everything from this part here, and then we'll call it a day already. We'll continue the rest of this chapter next week, guys. And that means there's no homework this week. Yay! Yay! Good thing. Oh, sure. Yeah. I'll see you next week. Bye. Yeah, for those who are done copying, you can go already, guys. I'll see you next week. Bye-bye. Oh, welcome. Bye-bye. Oh.